Here. Yeah, so let's see. On Thursday, we actually did cover a lot of ground. We remind you everything you knew about complex numbers, including multiplying by a conjugate on the bottom and top, and I to various powers, and just kind of refreshed your memory about those things. We talked about like complex numbers, a little bit of the history of I. We talked about plotting the complex numbers, and how we can represent them as two-dimensional numbers on the complex plane, with the real and imaginary parts plotted in the x and in the y direction. And thinking about that, we said, okay, well, x plus yi, we could maybe, instead of using rectangular form, we can think about polar form. And then we kind of left it at that. We said, isn't that interesting, right? And it was kind of just a curiosity. But today, we're going to really show you the power of doing that, of being able to write things in polar form. Why is that maybe really useful to us, is the question. So we're going to do some arithmetic today with complex numbers, and I think you're going to be won over pretty quickly on why polar form is really kind of slick. You ready? It's fresh, man. Yeah. That goes out to Jerry. All right, so let's consider multiplying two complex numbers, and suppose that I've given them to you already in polar form, all right? That is, let's call the two complex numbers I'm going to multiply z1 and z2, and I've given you them in polar form, in this form right here. R1 and theta 1 are known to you. R2 and theta 2 are known to you. And if you were to multiply those two numbers, let's just play around and see what we get. That is, this thing in polar form, there's z1 and z2. So far, so good? I think you'd be tempted, like I would, to factor out the R1 and the R2. Let's put those out front. And then I'm going to FOIL the inside stuff. You ready? So I'm going to actually, like, cosine, right? All that. The way I'm writing it, though, let's make sure that I've done it right, okay? Because I've done it in a particular order that I like, okay? I think this is pretty clear. This first piece, where that comes from, that's cosine theta 1, cosine theta 2. Okay, got that, Mr. Chase, I got that. Where'd this come from? Negative sine theta 1, sine theta 2. Which product is that? That's, got it. Okay, I and I, that's negative 1. Okay, I'm with you. So far, so good. Okay, what about this stuff over here? That's part of the product? Okay, I factored out an I. Where'd the I sine theta 1 cosine theta 2 come from? Is that up there somewhere? I sine theta 1 cosine theta 2. Got it. What about the last one? I cosine theta 1 sine theta 2. Is that in there too somewhere? That'd be sine theta 2 and I and cosine theta 1. Okay. Everyone clear on where every piece of that product came from? I did FOIL it, but I kind of put it in a way that I like. Because why did I do it that way? What have I color-coded? Do you see in red what I see in red? I mean, I highlighted it for a reason. It should be staring you in the face. It's the... Yeah, this is the cosine addition formula, and this is the sine addition formula for theta 1 and theta 2. So in red, again, I've just reduced that in blue. There it is. Okay? Which comes out to be really kind of, like I said, a pretty fresh result, really, if you think about it.
You tried to.
It's dope. It's a pretty tight result.
Your usage is
on fleek, is trying out all. I'm way too old for that. Fun facts. My birthday's this week, and I'm getting older. And also another fun fact.
Are you yet considered old, or that's
not, but depending on the standard, right? By the world standard, yes. By the American standard, no. I thought so. This whole week is. Did you see the fun fact about the dates this week? At least written in our form.
Yeah.
They're all palindromes. Every day this week is a palindrome. All right. So here are the two. Think about it. Okay. Revel in it as you go through the week. Okay. Yeah, and maybe some next week, right? Until winter. So the first result we just established is here, right? If you multiply two complex numbers in polar form, then what are you doing? You're multiplying the R values, you're adding the angles, though. Cool. All right, that's really kind of slick, kind of elegant. And then this result maybe follows pretty quickly behind it, right? If you divide two complex numbers, the R values get divided. The arguments get subtracted. Like you could maybe even prove that with this result, or like maybe maybe leave that as an exercise to the reader. See if you can prove that second result. But it's similar, you know, the same kind of idea. All right, so these are already maybe already you're starting to see why polar form is nice, right? If you were to multiply two numbers like old school, right? It'd be, you know, something plus something I times something plus something I. It's not that bad, but you have to FOIL it, right? You collect like terms and all that. That's not bad. So this is a little easier than that, I think. Dividing is certainly easier in polar form, for sure, isn't it? Because if you divide two numbers in standard form, something plus something I divided by something plus something I, you know, we've just been doing them. You did them in homework last night. You have to like multiply by like conjugate. I mean, it's messy, right? Dividing in polar form, though, will be a snack. Okay, so you don't need all this stuff. Just it's in the box here. There we go. In fact, everywhere you see this, you could write cis, right? 2. Cis theta 1 plus theta 2. If you like. Just to illustrate how slick this is, down this second result, like if you were to do 8 cis 71 degrees divided by 2 cis 20 degrees or something like that. You know, in rectangular form, that would be a mess, right? You have something plus something I, you have something plus something I, you have to multiply the conjugate on the top and bottom, you have to resolve the stuff in the numerator, you have to resolve the stuff in the denominator. It would be terrible. But here, it's just one simple thing, right? It's 4 cis what? Right? Done. Don't we like it? Don't we starting it? This is only the tip of the iceberg. Still need it wave wildly. Still do this. Let's see if we wildly. All right. So do it here. Go ahead and multiply these, and then plot the result too. I want to say a few things about why there's something cool going on here too that might be visual in nature as well. The product here is not hard to say. It's 35 what? Cis 70. Wonderful. So let's plot these things. How about in green? 5 cis 50. That's, oh, I don't know. How about here? Something like that. Call that 5 cis 50. 50 degrees at 5 units out. 50 degrees. I'll do this one in red. How about 7 cis 20? That's, I don't know. How about over there? 7 units out at 20 degrees. I'm just making stuff up. And then in blue, what's that? And then in blue, 70 degrees, 35 units out. So we're adding these angles, and this is not to scale. Right, something like that. All right, so maybe you're not like impressed yet, okay? Certainly, this is interesting though. When we multiply complex numbers, we're getting the magnitudes multiply, which is not a huge surprise maybe, but also their angles add, and so that we're kind of, multiplication in some sense corresponds to a rotation in the complex plane. This is very interesting. Let's think about that for a second, just off to the side here. I'd like to talk about this for one more moment, because I think this is a powerful idea. What would it mean to multiply your favorite complex number? Think of your favorite complex number. Multiply it by I, okay? And tell me what you've just done in the complex plane. What have you done to your point? Has everyone got their point in mind? Maybe your favorite point is 3 plus 4i or something like that. Multiply it by I and tell me where the new point lies. Where is it? What happened to it? It did move into another quadrant? Okay, cool. My favorite number is actually 1. It's a complex number, right? 1 plus 0i. What happened to my number when I multiply by I? It's a 90-degree rotation, isn't it? Which should make sense, because what did I do? If I'm multiplying by I, multiply by I. All right, this is fun, right? If we multiply by I, then I has, in polar form, that's cis pi over 2, right, is what it is in polar form, right? 1 cis pi over 2, isn't it, in polar form? 1 unit this way is what I is, isn't it? Maybe that's not obvious to everyone else. Okay. In polar form. All right. So when we multiply it by stuff, the R value of your thing that you're multiplying by doesn't change at all, right? Doesn't lengthen. Multiplying by I doesn't dilate anything. But it does add pi over 2 to the argument of whatever your complex number is, which does in fact correspond to a rotation by 90 degrees. So you want to rotate something 90 degrees? Multiply by I. Which sheds light for us a little bit on something that maybe has always been a little bit of a mystery to you. Like back in middle school when you learned to multiply by a negative number, right? You thought like, you know, I'm at the number 7 right now. That's where I'm at over here, at the number 7. If you're at 7 and you wanted to go backwards, you'd multiply by, I don't know, -1 or something, right? To kind of flip yourself. You might even say flip yourself, I don't know, 180 degrees, you might say, right? If you wanted to rotate yourself by 180 degrees, you'd multiply by -1, wouldn't you? Wouldn't you? Okay, so I think you all agree with that. Why do we want to go just 180 degrees then? I think it's natural to ask, what would happen if we wanted to not go 180 degrees from where we are? What if we just want to rotate 90 degrees from where we are? Now, in middle school, if you were learning about negative numbers, that might not occur to you because you'd be like, that would put me off of the real number line, right? But that's a perfectly legitimate question, right? And the answer is we multiply by I, all right? So now we're up here at 7i, 90 degrees away. And then you're like, well, actually, I did want to go 180 degrees. I'd like to come back here. So maybe I'll multiply by I again, right? So the question is, like, if you wanted to go 180 degrees, that should correspond to 2 multiplications too, shouldn't it? It should multiply. You should be able to multiply by something. I don't know what yet, because I don't know anything about complex numbers. And that should take me 90 degrees. And I should multiply by it again, and that should correspond to doing the 180 degrees. So even if you didn't think about complex numbers, you should think that maybe there's something that there's something that would fit here. And if you didn't know anything about complex numbers, you might discover them by thinking about this, right? And of course, the number that belongs in these question marks is I, right? So I is that 90-degree rotation that you need. And of course, you can rotate by other things too. But that gives you that 90-degree rotation. So that's maybe a nice justification that brings us back around to negative numbers and makes you more satisfied with your middle school discussion of negative numbers. Yeah, it's cool. All right. Back to your regularly scheduled programming. Sorry, I got a little excited there. All right, go ahead and do this one here. And both of these are ones you can do right now. We'll reconvene in a second. Read the directions carefully. If it says put your final answer in standard form, do it. If it says polar form, do it. So in polar form, what are we getting? 6, cis, something. Yeah. Everyone add those two arguments together. You get 6 cis pi. And just because we're still a little bit new at polar form, maybe we actually write this out again. Maybe instead we write 6 cosine pi plus I sine pi. So what does that come out to? 6. What's the cosine of pi? And the sine of pi is, all right, so what does that come out to? And maybe you, like I said in the warm-up, I want you to start thinking about these in a more intuitive way, hopefully. I mean, it takes some practice to gain intuition, maybe. But do you need to like do the conversions that we did in the warm-up? I mean, do you really have to go through this process? Do we need to show this step and this step? Maybe not, right? Just think about what this means for a second with me. 6 cis pi, 6, that way. Where are you? Of course you're at -6, done, right? You can also evaluate the cosine and the sine and blah, blah, right? But it's all, of course you're at -6, just think about it. So you don't need to show any of this work in the middle if you don't want. You just think about it. What am I asking you to do? Z squared over W. Whoa, okay. All right. Where the Z and W are these things. All right. So I'm asking you to do 15 cis 75. That's what it means to square something. All over 5 cis 100. Does that help, right? To write it that way. What order do you want to do this in? I don't know. It doesn't matter, right? I'm kind of interested in killing the 15 here, making that a 3. So what do we got? 45. On top, what is that? Cis 75 times cis 75 is cis 1, 75 times 2, right? All right. Over cis 100. What do we get here in the end? What do you get? It says leave your answer in polar form, so that's good. We just get 45 cis 50. I mean, you could have done it some other ways too. You want to multiply the top two, you get 225 cis 150, and then do the whatever. Whatever order you do this in, hopefully we're all getting the same result, right? Okay. Again, stop and think about how difficult this would be if I had given you, instead of Z and W in these forms, if I had given them you in A plus BI form, right? This would be a different problem. But here, if they're in polar form, it's awesome, isn't it? Feels great, doesn't it? It really, so weird. Multiplying stuff, we're actually doing some addition. And dividing things, we're actually doing some subtraction. It's so weird. Almost sounds familiar. All right, let's keep going. The following result, like, really immediately follows. I mean, you just thought about what it would mean to square Z. Well, what does it mean to cube Z, or to Z to the 4th power, or something like that? Could you do that? Sure. Right? In polar form, that's not hard at all after our previous result. You know, what did it mean to square the last number? Well, of course, R gets squared. But then we have, instead of 75 degrees, it was 2 times 75 degrees. It's 75 degrees plus 75 degrees, wasn't it? Or in general, n times theta, isn't it? Because you have n copies of theta in your sum. So it's just n theta. So I think this just kind of nicely follows from the previous result. But if you wanted to prove this more rigorously, you might, right? I mean, we got to do a real quick proof for n equals 2, couldn't we? What about n equals 3, though? Could you do a little proof of that? How about you prove it for all n that this holds? Yeah, maybe using like some proof technique we've learned recently. All right, try that. Try that when you have a spare moment later today. Try proving this result. Okay. Regardless of whether you prove it or not, it should still be intuitive to us, right? It's just, we've already taught you how to multiply, so this is just a special case of multiplication, isn't it? Okay. And with this, we've jumped into something really powerful without you even noticing, really. I'll give you a problem now, and notice that if I were to have given you this earlier, this would have been pretty daunting. Like if I gave this to you, something plus something I raised to the 5th power, you'd have been like, I'll see you in 20 minutes, right? Right? But in polar form, we're like, oh, done. I'm done already, right? What is it? what's it going to be? This is 2 cis pi over 6 times 2 cis pi over 6 times in polar form, if I have it written that way. This is really trivial because of this little theorem. Of course, this will be 2 to the 5th. That's 32 times cis 5 pi over 6, right? It's just 5 copies of pi over 6. Beautiful. That was actually the easy part. The hard part now is like getting this back into rectangular form and thinking about our trig from first semester. All right, so that'd be 32, because it does say put it in rectangular form, so let's do it. That'd be 32 times the cosine of 5 pi over 6, which is, cosine of 5 pi over 6 is negative root 3 over 2. And the sine of 5 pi over 6 is positive 1/2. All right, and then let's maybe clean that up a little bit. Let's negative 16 root 3 plus 16i. Okay, which actually suggests something else to me. It says if someone gave me this original problem, which let's see, if in rectangular form, if they'd give it to me in rectangular form, which is root 3 plus I. Say someone asked you to do that. Hey, take root 3 plus I and raise that to the 5th power, right? Instead of doing that, I might actually, even though they gave it to me in rectangular and they want the answer in rectangular, I might actually drop into polar, do the arithmetic, and then come back to rectangular, right? Because this was so easy, right? Do you agree? Like polar is that useful that even if someone gave me something rectangular, asked me to do something, and then asked me to put the result in rectangular, I might actually go through polar even though no one asked me to, right? So that's my suggestion on this next one too, right? Yeah.
Where do you get cis from? Is it like the c, the cosine, the i, the
I sine, yeah. It's really kind of sloppy actually, but we'll go with it. So it's quicker to write, huh? I mean, I think most people would understand it. It's not. It's like when you're taking a course in complex analysis, you'll do something a little slicker, and I'll show you before the class. But yeah, Joshua.
How is this really a theorem? Like, isn't he kind of just stating what the basis and the multiplication?
Yeah, it's really just a special case, right? I mean, you don't want to even put it in a box. You don't want to give it box status, Joshua.
But like, I don't think that guy should get a theorem.
You're right. He doesn't really deserve it. I don't know. He actually, we have a history of naming things after on behalf of other people. I don't think he gave it his own. He just named it himself. By the way, de Moivre is how you say that. De Moivre's theorem. De Moivre. It's another French guy, right? It's all the French guys. What do you think his name was? Probably like Jacques, right? Or like, yeah, or something, right? Right? Wrong. It was Abraham. Abraham de Moivre. There you go. A little French-Jewish action going on there. Okay. I don't know. I said, like, I don't know. That's true though. I'm not lying. His name is Abraham de Moivre. So, all right. So, did I give you a hint as to how to approach this then? Even though I've given you something rectangular and I want the result in rectangular and I want this to raise to the 4th power. Thank you. I want, maybe we might do what to this guy first? Before we do anything else, we might be like, hey, wouldn't it be fun to express this in polar form? And I've made it nice for you, haven't it? Haven't you? What's R? 1, can you tell? I mean, this is just, hopefully you're, again, don't reach for the formulas. Don't be doing the square root of this thing squared plus this thing squared. You're welcome to, but you'll get 1. Okay. You should just recognize this as a point on the unit circle, right? So it's, yeah, 1 cis, what angle is that? 3 pi over 4. Okay, and now I think I'm ready to take this to the 4th power. So w to the 4th is, instead of this thing to the 4th, is cis 3 pi over 4 to the 4th. I like that. 1 to the 4th is 1. And cis 3 pi over 4 to the 4th, let's see. It's just cis 3 pi, right? We multiply this guy inside here by 4. Or cis pi, if you like. And so what is that? Well, what is it? Is it just clear to everyone that it's -1? I hope it's starting to be clear that that's just, oh, pi in the direction of pi. Oh yeah, 1 unit. I got this. It's -1. I mean, if you're still not with us, it's just cosine 3 pi plus I sine 3 pi. This is 0 and this is -1, right? Okay. But again, just start thinking intuitively about it. This should shed a little bit of light on those problems I gave you on Thursday. Do you remember? Those two problems that I gave you that worked out really nicely. Maybe now you can see why, right? Yeah? You know what I'm talking about? The ones that came out, so like one of them came out to 8, I think, and the other came out to 64i or something like that. Okay? Cool stuff. Are you ready for an amazing fact?
Is this like your joke?
No, this is actually an amazing fact, sorry. Okay. Alright. By the way, this is like really one of our very last lessons in pre-calculus. We have one more on Wednesday, really, to round out this unit, and then we have kind of review other stuff we're going to be doing. So this is one of our very last, and this is a very special moment at the end of this course, right? So to be able to share this really incredible fact with you. Are you ready? It's going to blow your mind. Okay? Can we get a little drum roll, maybe? Yeah, you're like, what? That wasn't very climactic. Yeah, it is. I'm going to convince you. This is called Euler's equation, named for Leonhard Euler. In this box here. Here it is. I wrote it up here, but of course here it is nicely in a box. The r is not the important part, but this part here, e to the I theta. What? E? Yeah, e. That e. E to the I theta equals cosine theta plus I sine theta. An incredible result. Which makes me think, earlier when we were like doing, cosine of, or if I were saying, what was it, cis? I'll just write cis here. Cis 3 pi over 4 times cis pi over 4. Instead, you could be thinking, and you know what that comes out to, cis pi, right? You get -1, right? Instead, you could be thinking, well, this is e, by this new result, this is e to the 3 pi over 4 times I, and this is e to the pi over 4 times I. And so, of course, all the results from today are just trivial, because didn't we kind of see this coming, maybe? When we multiply, we feel like we're adding. When we divide, it feels like we're subtracting. That sounds very familiar to me, because you know it from your laws of exponents. That's really what's happening here. What do we get? E to the pi I, which you could write as cis pi, if you like. Whatever. It's -1, though. Okay. So that answers this question. What happens if you let r be 1 and theta be pi in this formula? You get the thing we just said, right? E to the pi I equals what? -1 is what you get if you just plug this in. Sometimes people write it this way. And this is sometimes called Euler's identity sometimes. Euler's equation is the more general and beautiful thing, really. But this is astounding, and this is the kind of thing that like you might get a tattoo of someday or something like that. Look at it. Just look at it for a second. Stare at it. Ignore all else on this slide and just stare at it for a second. This relates e and pi and I and 1 and 0, like the 5 of the most important mathematical constants that we know and love, right? All in one equation. It's beautiful, isn't it? And then I want to leave you one thought. I see some hands. But I'd love you to, this sounds like magic, right? But could you prove it? Could you prove it? Maybe using some other things we've learned about recently? Could you prove Euler's identity? Using 3 infinite series that you know and love? Right. All right, I love you all. Bye.
Isn't it also called God's equation?